Machine learning is a subset of artificial intelligence that enables computers to learn from data without being explicitly programmed. Unlike traditional programming where we write rules, machine learning algorithms discover patterns and rules automatically from examples. It's the technology behind recommendation systems, image recognition, voice assistants, and self-driving cars. Machine learning has three main categories. Supervised learning uses labeled data to predict outcomes, like classifying emails as spam or not. Unsupervised learning finds hidden patterns in unlabeled data, like customer segmentation. Reinforcement learning learns through trial and error with rewards, like training robots or game AI. In supervised learning, we train models using labeled examples. Each example has input features and a known output label. The algorithm learns the relationship between inputs and outputs. Common tasks include classification and regression. It's like learning with a teacher who provides correct answers. Linear regression predicts continuous values by fitting a line to data points. Perfect for price prediction. Logistic regression predicts probabilities for classification tasks like yes-no decisions. Decision trees make predictions by asking a series of questions, splitting data at each node based on features. Random forest combines multiple decision trees to improve accuracy and reduce overfitting. Support vector machines find the best boundary to separate classes in high-dimensional space. Neural networks mimic brain structure with interconnected layers, excelling at complex patterns in images, text, and speech. Unsupervised learning finds structure in unlabeled data without predefined categories. The most common task is clustering, which groups similar data points together. Applications include customer segmentation, anomaly detection, and data compression. The algorithm discovers patterns we might not know exist. K-means clustering partitions data into K-groups by finding cluster centers and assigning points to the nearest center. PCA reduces data dimensions while preserving important information useful for visualization and speeding up algorithms. Both are foundational techniques in data science. Every ML project follows a systematic workflow. First, collect relevant data. Second, clean and prepare it by handling missing values and feature engineering. Third, select an appropriate algorithm. Fourth, train the model on training data. Fifth, evaluate performance on test data. Finally, deploy to production and monitor. We split data into training and test sets. The model learns from the training set and is evaluated on the unseen test set. This prevents overfitting and ensures the model generalizes to new data. Common splits are 80-20 or 70-30. Never test on training data, or you'll get misleadingly high accuracy. Classification models need proper evaluation. Accuracy measures overall correctness but can be misleading. Precision measures how many predicted positives are actually positive. Recall measures how many actual positives we found. F1 score balances precision and recall. Choose metrics based on your problem's priorities. Regression models use different metrics. Mean absolute error, MAE, measures average prediction error. Mean squared error, MSE, penalizes large errors more heavily. Root mean squared error, RMSE, is MSE in original units. R-squared indicates how much variance the model explains, where 1.0 is perfect. Overfitting occurs when a model learns training data too well, including noise, and fails on new data. Underfitting happens when the model is too simple to capture patterns. The goal is finding the sweet spot with good generalization. Techniques to prevent overfitting include regularization and using more data. Feature engineering is creating new features from existing data to improve model performance. It includes encoding categorical variables, scaling numerical features, and extracting information from text or dates. Good features often matter more than complex algorithms. Real-world data often has missing values. You can remove rows with missing data, but you lose information. Alternatively, fill them with statistical values like mean or median, or use algorithms to predict missing values. Choose based on how much data is missing and why. Cross-validation provides more reliable performance estimates. K-fold CV divides data into K parts, training K times with each part as the test set once. This ensures every data point is tested and reduces variance in performance estimates. Hyperparameters control how algorithms learn. Grid search tests all combinations of specified values to find the best performance. Random search samples randomly for efficiency. Finding optimal hyperparameters significantly improves model performance. Bias is error from wrong assumptions, leading to underfitting. Variance is error from sensitivity to training data fluctuations, leading to overfitting. High bias means consistently wrong. High variance means scattered predictions. The goal is a balance. Python dominates machine learning with powerful libraries. Scikit-learn provides classical ML algorithms. TensorFlow and PyTorch are frameworks for deep learning. Pandas handles data manipulation while NumPy provides numerical operations. Machine learning powers countless applications. Healthcare uses it for diagnosis, finance for fraud detection, retail for recommendations, transportation for self-driving cars, and security for threat detection. Start your ML journey with simple algorithms. Always explore and visualize data first. Split data properly and validate thoroughly. Keep learning through practice on Kaggle and building your own projects.